doing? All right. Morning, my name is Sam, and today we're going to be talking about the refrigeration cycle results that Group 1 had got last lab. Talking about the coefficient of performance, what is it? And it's going to be the ratio of the heat or the cooling that was generated over the work that was inputted to get that heat. An increase in the COP means a decrease in your operational costs. So you can see this would be an important term to know when making sure you're reducing your costs as much as possible. And another note that it can't exceed over 1 or 100%, which is quite strange for most things where you wouldn't think 100% efficiency was possible. And that's because the heat that is produced is used by different components, and the other components can actually kind of, to an extent, reheat things. And so this is where you get your extra energy, I would say. Looking at the refrigeration cycle, we have our thermoplastic cycle there, and I just pulled the diagram from the manual as well, and the circles are the temperature and pressure points that we're going to be measuring at, or that we did measure at. And so we can see that our work in here at the compressor goes to our condenser and to our expansion valve and then our evaporator. So this is the basic cycle. And then here we have our compressor going to our condenser, and there's our expansion valve and then our evaporator. And this expansion valve is a little bit different than the basic just mechanical kind of expansion, where it actually has actuating parts that to an extent control flow rates and pressures. And we'll talk about that in a little bit too. So ideal versus real cycle, I know we've seen these a couple of times now, and I think I'm the last one to present on it, so we won't harp on it too much. But like most of the groups have said, the main difference is that in real life, the irreversibilities aren't possible. So it changes the graph to an extent where you lose some power and efficiency compared to our ideal cycle just because of these real life problems. Looking at a graph that somebody might look at when dealing with things like this, I thought that the goal of this was to pick the most confusing graph with the most lines. So I picked this one. And so they have a bunch of different variables that somebody might want to look at on the same plot, so we wouldn't just be able to find like our pressure and our enthalpy. Somebody could find their point on this graph and find other values that might be important to calculations without having to actually manually do the calculations. So I thought that was important. This is kind of like the one that we used. I'm not sure if it's exactly the same for our thermostatic expansion valve. And we have an exploded view of it. So kind of the key important parts is going to be this sensing bulb and capillary tube, which is connected to this power head and diaphragm. And so, and then right below it, we'll have a pin and then a spring. And so they kind of work to balance each other out. And in this slide, you can see that we have the hot, high pressure liquid coming in. And this is the expansion part. And so this whole mechanism moves up and down, or can move up and down. And the way it does that is after it goes to the expansion part in the evaporator, they use a sensing bulb. And so depending on the temperature in this tube, this liquid inside, which is kind of like a separate system, a closed system, it will heat up and vaporize this liquid in here. And then the more fluid that we have pushing on that diaphragm will, it's working against the pin, so it'll push that pin down and allow for more liquid to pass through if the temperature is too high. So it kind of works to regulate the temperature and try to keep it consistent when it's coming out over here, which I thought was pretty interesting that they do make electrical versions of this, but as a mechanical engineer, when you see things like this that can actually not think, but adjust itself based on what's going on in the system to get what you want on the output, I think that's pretty cool. So for exercise 1, these were our results. Anybody was interested in looking at it. And then we have case 1, 2, and 3 at our different flow rates. And so I noticed that the other groups were pretty consistent and on point with their numbers. They stayed pretty consistent through the cases. Ours did change a bit compared to theirs, and I was wondering if that was because we could have waited longer, I guess. Maybe the system didn't equalize. So that was just one of my thoughts that I had about why our numbers might have been changing throughout. And so for sample calculations, we were looking for our COPs. So we had to calculate our heats. And so this is just where we take our volumetric flow and convert it into our mass flow rates. Then we have our specific heat, and then our temperature differences. And then our work net that was returned to us on the computer. And by the way, this is for exercise 1. So the really interesting part is when you look at your COP, you have your heat over your work. And so the way that you can kind of maximize your COP is by increasing the heat as much as possible and decreasing your work. Where if you kind of want a fixed system, it's kind of hard to decrease your work. But if you look at your temperature difference, that's going to be the main dictating factor about increasing your heat. So, if we had a higher temperature here or a lower temperature here, that would make our heat bigger, therefore making our COP bigger. So that's kind of the way you could think about it or play around if you're designing a system like it. So fairly low COP. And then comparing that to our experimental data that was calculated by our group leader, Kayla, last week, we can see that it was a little bit higher than what we had anticipated it being. But that's also because I know Kayla picked these numbers, some of these numbers. So like she picked a really high work compared to the work that we actually used, which, being on the denominator decreased it a bunch. But she did have a much higher difference in temperature compared to what we actually did. And I know she just picked those and wasn't sure exactly what they would be. So that would be my explanation. And wouldn't really say that the experimental data would help prove that we were on track just for those reasons. Measuring uncertainty, I couldn't find much on it besides for the resolutions. We knew what the resolutions were, so we just did our resolution uncertainty. And here was the numbers that we had used, and we converted our volumetric to mass flow here. And then, like we do in instrumentations, doing our propagation of uncertainty, got 0.5, 0.15, and 0.37. So I would say that that's, for the COP, it's a little high, just for the fact that it was, 0.06, I believe it was. So that kind of changes the number a lot. And the work was 0.404, so, the heat was, I forgot what the heat was. So the heat was also pretty low. So I would say that those are both very high since they can change the number quite a bit. And my references, if there's any questions.
Slide 10. What did you use as 4.25?
That was the density of the refrigerant that I found online. That was because we were in liters per minute, so volumetric flow, and we were looking for a mass flow. So we had to find a way to cancel out our meters cubed to get it in kilograms per second.
Should it be density of the refrigerant?
Or should it be density of water?
As I'm thinking of. Slide.
Now I want to think about it.
It's okay. I just wanted to be sure.
Yeah, I guess if we're looking at the temperatures of the water, right, then we would want our density of the water too. So that's my mistake. I don't know the value off the top of my head.
Because when you also check CP, what CP did you use?
What was that?
CP value.
Which CP?
Oh.
CP 4180. I believe that should be for water.
Yeah, it's probably for water.
So I think we just got.
Yeah, so this
use
is,
CP for water.
this should be the density
Use
of the
density
water.
of,
Mhm.
the refrigerant. So that's probably the reason why your results were that small.
All right. All right, so, like you said, this should be our density of the water rather than the refrigerant. And, then the numbers might come out a little prettier, I don't know.
It'll be a lot bigger, the density of water's like 1,000.
Okay,
Because it was water, then that should be like 1,000.
so it should increase by
Increase, yeah. So
about
almost-
3 decimal points.
So it should be like, one, close to, at least
Right.
less than 10.
All right, well, that makes me feel a little bit better. I was looking at them, comparing it to other groups, and like, dang, you know, they got some pretty good COPs compared to mine. But, all right, density of water, that's a trick. All right, thank you.